Alright, so I'll get underway. Yes, as I said, the plan is 45 minutes, 5-minute break, another 45 minutes. If we're going quickly through it, then we might just end up just doing it in one go. It looks as if it's going to be a bit quicker than that. But the first part is background, it's where current things are, looking at things you need to know and about, and then the second part looks at more at why they are the way they are and a solution or a way of doing things to get around some of the issues with reliability. So we'll get straight into it. Right, so what we have here is 10 studies pulled from the literature. It wasn't a systematic review, it was just have a look, grab, find 10 studies with 10 or more participants that presented normal gait, knee kinematics, ankle, knee flexion extension, abduction, adduction, and knee internal external rotation. As you can see, the means have been plotted here, reasonable. We'll find out later, and looking at it, that there's little relationship between what has been presented as normal knee, abduction, adduction, rotations during the gait cycle from heel strike to toe off. Even more so in knee internal external rotation, no relationship or commonality between the different studies. And these are the means that have been plotted. Okay, it's not individual data. Individual data were plotted, then the spread would be larger. So these are the means of 10 or more participants, as presented in the literature as normal knee kinematics. There's little resemblance to one another, or as we'll see later, little resemblance to normal knee joint kinematics. If you look on, these are all marker-based studies, by the way, with cameras, reflective markers. If you go on and look at radiographic bone pin studies, which are supposedly the criterion, the gold standard, there's not so many studies. Here we have individual data plotted rather than the mean. There's not so many studies and not so many participants. Same thing. Little agreement here between normal, what normal should be, and internal external rotation, little agreement there either of what normal should be. And if you look at those and bone pins and marker-based, they suffer the same problems of reliability and validity. And it's not, in this case, it's not related to skin movement artifacts. So as a criterion measure, you have to say no. It's just as unreliable as the marker-based studies.
Alan, how close is the sagittal one there? How close are the bone ones to the marker-based one? You look at it. That's okay. Just for the sagittal one. Yep. On the bone one compared to the marker one. On your previous slide, are they similar?
Extension. They're similar. Okay, so going from around 20, just over 60, and
they are pretty similar. Yeah.
Quite similar. Over 60, just slightly under 20, but quite similar. Yep.
When you say that the bone pins are unreliable, is that true reliability, or is it that there's actually quite a lot of variability within the way that people move?
And we'll see later. We'll as we go through and we address the issues. Cool. This will come clear later. Sure. We're looking at the data here. This is normal. What they're presenting, individual studies presenting as normal, and we can see. For now, we can just look at it and say there's little agreement as to what is normal, and they're all suffering from some errors, some rather large errors. And in this case, it's not related to skin movement artifact. So, yeah, we'll see later. We'll come back to this. We'll revisit this data later and actually see that there is an underlying common knee joint kinematics. Okay. So, one of the things we have to touch on To begin with is reliability. Reliability is fundamental to movement analysis because you need to know whether there's a change that you see, whether you can attribute to an actual change in movement or that change is just a reflection of artefact and the errors in your system. So it's a fundamental thing that needs to be established. So how many centres have actually done clinical or research have done a reliability study? Well, compared to how many appear in the literature to how many studies do how many centres do three-dimensional motion analysis studies, very few. How many have understood the results? So how many would understand what an ICC or a correlation coefficient of 0.855 or average standard deviation of 2 point something degrees, what does that mean? How does it relate to minimum clinical important difference? Or does it describe similar, different or unrelated paths? This type of understanding just isn't there in the literature. Okay, so how many would actually understand the results? Very few, if any. Okay, going on to reliability. Again, we're just touching base on a few things to begin with. Intrasession. Okay, so we have someone come in, we put markers on them, they walk up and down, you collect half a dozen gait cycles, or a dozen gait cycles, some intervention, and you test them again. Same day, same marker set, 2 sets of data. This representing a mean of 1 set of data before intervention, spread of data, again, 95% confidence interval, standard deviation. Another set of data after the intervention, whatever was in the middle, and 95% confidence and standard deviation. Okay, so intrasession. An easy way just to tell whether this data that you've got out are similar or the same or different, basically they're the same or different, is just to look at the 95% confidence interval. Okay, so if they're separated, they don't overlap, they say, oh, they're different. If they overlap, you can say they're the same. So it's a simple yes, no, same, different. 95% confidence interval, do they overlap or don't they? So the minimum discernible change, is up there, is the minimum change that you could be able to distinguish if you had a set of gait joint angle paths. And using the same rationale, we can say that, okay, if we have 2 means, 2 sets of data, standard deviation, then 2 times the 95% confidence interval would be our minimum discernible change. If the difference between the means is less than that, the confidence intervals overlap, and you won't be able to tell if there's a difference or not. So minimum discernible change we can define by the 95% confidence interval. Okay, if we did the same thing, intercession. So here they've come in, put the markers on, you collected your gait data, they've gone away, some intervention sometime later, they've come back into the lab, a different day, reset up, re-put the markers on, retest, and we get the same mean standard deviation of data. We can't in this case say that they are different. Okay? It'd be incorrect to base that same or difference on the standard deviation within each trial. Because if that was one day, that was another day, and if it was the same person, nothing had happened, and then they came back on a 3rd day, and a 4th, and a 5th, and you tested them, you'll suddenly see that, if this was the same person on consecutive days, this is the variation that we're getting, and all things being equal, that person hasn't changed. So if we're just looking at the healthy subject coming back on consecutive days. So on consecutive days, we just can't look at the means and the individual data that was obtained on that day. We've got to look at a reliability study, intercession reliability, which gives us an overall picture of the intercession reliability, spread of data, or the 95% confidence interval, or standard deviation across consecutive days. So now we can look at the data that we had and we look, are they the same or are they different? Well, according to the 95% confidence interval, but if we're doing studies, if we have them come in on one day and test them, on another day and test them, and another day and test them. So we've got 3 pre-intervention. Have the intervention, then they come back. Test them once, test them twice, test them 3 times post-intervention. We then have a mean, a group of tests, group of values, the mean of each. We have means, and we have a 95% confidence interval. Then we can use a 95% confidence interval. Okay? But if they come in once, which is typically what happens in clinical studies, because it's inconvenient to get people in multiple times before and multiple times after, usually it's just one. One time before, test, intervention, sometime later, one test after. So in this case, you haven't got a mean and a mean, you've got a single value and a single value. That's all you've got. So then, our minimum discernible change on this instance, we have to use a standard deviation, which is the spread of the data to tell whether these 2 data that we got, pre and post, are in fact could be considered as part of the same data or separate sets of data. And so for that, we're using, that's 2 standard deviations, this is 4 standard deviations. So we're using 4 standard deviations for our minimal discernible change if we have a single value pre and a single value post. And in terms of data analysis, that is 1 session pre and 1 session post. So we've got 2 alternative definitions of the minimum discernible change. If you have a group of measures, an intervention and a group of measures, both groups under similar conditions, like intra-session, you can base it on the minimum discernible change on the 95% confidence interval. But if we have inter-session and we only have 1 measure before or 1 measure after, we have the spread of data, our standard deviation information from our reliability study. We've got to look at 4 times our reliability study to tell whether these 2 measures are part of the same set, the variability that you would expect of the same individual being tested repeatedly, or in fact different sets. So that is a weakness of clinical studies, and a quick, an easy way to increase reliability of clinical studies is to test the person multiple times before and multiple times after, but on multiple days. But that's just impractical in most cases to do that type of thing. Okay, so we're moving right along. So that was some reliability stuff. Outcome measures. There are a range of outcome measures commonly presented. We've got ICC, interclass correlation, CMC, the coefficient of model correlation, average standard deviation, RMS, and standard error of measurement. The last 3 measuring the within subject variation in degrees of rotation. Okay, but ICC in the literature, we find that 0.7 to 0.8 is defined as fair, satisfactory, acceptable, good. There are some differences there. I'll fix it up one day and put the actual things there. But generally to say, we're 7 to 8, we're in that fair, satisfactory area. 0.8 to 0.9 is reported as high, and greater than 0.9 is reported as excellent. General overall assessment of ICC in the literature. The problem is that they are arbitrarily chosen. There's no scientific basis for it, no clinical basis at all. It's other than it sounds about right. That's it. The whole reliability studies and reporting reliability studies is based back to these values which sound about right. 0.8 sounds good. Oh yeah, 0.9, well, that sounds very good. There's nothing behind it. And also it's applied to all joint angles. And you can't apply a correlation to all joint angles with one value. There's a huge variability in range of motion. You take a knee, which is anywhere from 60 to 70 degrees, to knee flexion, to knee abduction adduction, which is somewhere around 5 degrees, 6 degrees. So there's a factor of 10 there between ranges of motion. That influences R, and what R needs to be reliable. And then you've got all the other joint angles that are in between, from 6 to 60. So going around 45, and some around 20, and some around 12 and 10. So I've got a wide range of joint angles, all needing specific correlations. So a correlation on one joint angle cannot be compared to a correlation on another because of the wide variability in the joint ranges of motion. We'll see a bit more on this later. The problem is the lack of any criterion or critical values in the literature to measure reliability outcome measures. Okay? So this is kind of highlighted. A few of these through the talk, the yellow bits highlighting key points. The lack of a criterion, something solid, based foundation for judging outcome measures. The consequence of no criterion, well, there's some there. One is, irrespective of the outcome measures, all reliability studies generally find, yep, that's reliable. It's either, well, it's reliable, it was okay, it was, in the good to satisfactory, which was down low, well, it was, it was described like that, okay, oh, it must be reliable. It's comparable to the others who've done similar studies, have got something around, 0.7s, 0.8s, oh yeah, it's reliable. So, calling it reliable, but they've got no basis for it. The other thing, this is probably even more important, without a criterion value gives you a goal, it gives you something to aim for, somewhere where you should be. Okay? Without that, there's been a lack of critical evaluation of the literature. It's just accepting what's there. But if there's a criterion there, you say, oh, well, we can't accept what's there. It gives us a reason to critically evaluate the methods, reliability, and even usefulness of these methods, even as a research tool. And also, the lack of a goal has hindered, well, it's taken away the desire, the need to search for alternative methods. The people just going along happily doing what they're doing, presenting, a few reliability studies there are, presenting measures and saying, oh, well, this is okay. So there's some consequences there of not having criteria. I mean, this is just one I just pulled out of the literature, a reliability study. You want to name on it, it's not pointing fingers at studies, but it's common. Produced higher repeatable frontal transverse, like non-sagittal plane rotations of kinematic data compared to previous studies. Again, compared to previous studies. It turns out, that their reliability data wasn't actually that good. It was just better than the ones they compared it to, a selection they compared it to, which were even worse. Okay, we'll move on from that. Okay, so criterion values. So we're getting into, okay, we need to do something here, we're getting into some work. So we need criterion measures against which to measure reliability. We need to judge whether outcome measures are sufficient to meet some minimal clinically important difference. So these are our average standard deviation, coefficient of model correlation, ICC. And describe whether these curves, they describe something which is similar, or same, similar, different, unrelated, identical set of curves. So you don't get a set of curves walked up and down, there they are. We've calculated some variables, but what do they mean? And that's what we need to establish with our criterion values. Okay, the first thing is to define the minimum clinically important difference. Now, in the literature, there's very little on this, but there is some reference to the knee, and the knee clinically important difference of 5 degrees, which means that anything under 5 degrees for knee flexion extension, yeah, we're not so interested. Anything over 5 degrees of knee flexion extension, yeah, we want to be able to see that and document it and be able to say, yeah, we've seen it. So for the knee, there's some research and some references, well not research, but references at least to subjective 5 degrees being the minimum clinical important difference for the knee flexion extension.
With those studies, have they divided, say, obviously knee flexion extension, sagittal plane has big ranges, but most of that range comes through swing?
Yes.
Have they, but swing phase is usually not really what people are most interested in. And therefore, do they actually divide it out and go, okay, well, since it's stance that we're largely interested in, and therefore the potentially 5 degrees is quite a big part of that
exactly where you're going with that, and we'll see this as we go along, that for the knee especially, in flexion extension and your abduction and your internal external rotation, there's much less range of motion during stance and an increased range of motion during swing. Not so much with the hip 3 right there, there's not so much there, but knee especially has quite a distinct difference between stance and swing as to range of motion. Ankle, yeah, also, but probably knee's the most pronounced. And okay, all this, what we're doing today, has been looking at an overall criterion values. And that's one of the things we come back to, the Kelly's mentioned, one thing we come back to at the end is, okay, now that we've done this, we're really, okay, for the knee, should we actually be dividing this into stance and swing phases? So that's something we'll come to later, but it is a definite an issue there.
Sorry. So, based on the reading that you've done, the 5 degrees is based on what?
Again, it's subjective. It appears in the literature, referenced a few times. It's subjective. It's people working in gait analysis with our clinicians, biomechanists, movement analysis, looking at gait analysis, and
so
there's
no evidence for that to being related to anything in terms of prediction of injury, chance of getting more symptoms, nothing.
No, it's just a subjective by people working in the area that 5 degrees appears occasionally, mentioned as being a reasonable. So people looking at gait assessments, looking at movement analysis, saying 5 degrees. Yeah, I think that's about right.
What are they basing that on when they're thinking that?
I don't know what they're thinking of. But I mean, I'm happy with 5 degrees as well. I mean, you could look.
Why are you happy with 5 degrees?
Actually, that's something.
What are you thinking when you're happy with 5 degrees?
Actually, I'm not. Because what Kelly said is right. The swing phase where you're going up, 60, 65, 70 degrees, if you see a 5 degree difference there, yes. But in the stance phase, you're going from a few degrees up to about 15, and down again, drops down to about 10, and then up again. So 5 degrees there, your minimum clinically important difference during the stance phase should actually maybe be a bit smaller than that.
I think the title of the term for a novice and a student is being very misleading, unfortunately.
The term minimum clinically important difference.
Unfortunately.
It is at this stage.
A student and a novice would read that and think that there is some clinical importance to it, which would mean that it's associated with pathology, which unfortunately is not.
No, but it is supposed to have clinical importance. It's been judged by experts, in the area, and looking at gait and saying 5 degrees seems a reasonable value. So there is some.
You can move on.
Yeah, we'll move on. So scientifically, in numbers and various things, no, there isn't. But in practical terms and just judgment of people working in it, it's a value which has been pulled out. Okay. So for now, I'm sticking with 5 degrees because I haven't got anything better to go with.
Neither have I. I haven't got anything better either.
Okay. Oh, here we go. Knee, 5 degrees. Okay. So then I work down knee, abduction, adduction, moving along, 6 degrees. And I just said, okay, 6 degrees. I basically did and put, 2 degrees for knee flexion extension. 6 degree range of motion, 2 degrees, a third of that. Okay, that'll be a, I'd want to see that. And then just put some values in relative to the range of motion for the others. Then I thought, that's not, the best. So to get a more representative value, a log transform was taken of the joint ranges of motion. We're going from 6 to 60, which cries out log transform. One's a power of 10 of the other. Do a log transform, fit a line to it, and then smooth out the values to get where all these decimal points came from. So it's just more representative of the log of the range of motion, or more representative of the range of motion by just fitting that log transform and a line through what I'd initially just estimated as being an appropriate range of motion. So that's just where it's come from. Range of motion, starting with some initial estimates, 5 degrees we need, and working the way down, then fitting a line through it using a log of the range of motion and coming up with decimal points. Okay, so it's not scientific, it's a bit of just judgment, but at least there's some values or something to start working with. Criterion values. Okay. Minimum discernible change. Okay, so we've kind of put together some minimum clinically important differences. The minimum discernible change, again, we covered this in just earlier. So there's two kind of variations. One's intra-session based on a mean compared to another mean, set of data, same, similar setup between the both. Standard deviation, two standard deviations. There's one definition of minimum discernible change. The other definition, we have a set, but they're not the same conditions each time. It's changed in between. So we've got a single value, if you're looking at like clinical type studies. And the other definition then is based on 4 times the standard deviation. So there's 2 variations there for the minimum discernible change. So then what was done was for all joint angles, so there's 9 of them, hip, knee, ankle, flexion, extension, abduction, adduction, internal, external rotation. There are 60 set of gait curves for each. That's 540 odd gait curves. So then there's example 1, there's another one. They're pulled from a large pool, 10 subjects, data measured from 10 subjects. They included curves that came from the same subject on the same day, the same session. It included curves between subjects on different days, and or the same subject on different days, and curves from different subjects. So the big variability. So the idea here was just get a big range of gait curves for each joint angle with a wide variability of similarity or non-similarity or differences in those curves. So there's a big pool of data. Then for each curve, they were subjectively rated. Now this comes up a few times already, and it's coming up again. A subjective assessment from identical, similar, different, unrelated. Okay, so they're all that's done. So there they are. Went through, ranked them all, and calculated the various variables that we have. The average standard deviation, the CMC, and the 2 variations of the minimum discernible change. So all of these were calculated for every set of curves as well. Okay, so then, to get the criterion values which separated curves into identical, similar, different, unrelated, was reasonably straightforward, I suppose. Rank them according to minimum discernible change. It should be either one. I use the 95% confidence interval. Rank them all. Well, I should use both. Rank them all, and then look. Rank them by the minimum discernible change, that is, and then look at whether they were ranked as similar, different, or unrelated. When they're all ranked, you'll find there's a whole group of similar. There's a bit of variability where they're being described as similar or different, and then there'll be a group that's described as different. Okay? So there's kind of a change from similar to different. And look in the middle. This is going to be our criterion, our 2 by 95% confidence interval, or our 3 by average standard deviation. Our values representing a similar gait curve. Okay, so a whole lot of great gait curves ranked as similar, different, unrelated. These values calculated from the whole lot, ranked in order of the minimum percentage change, and then you look at where the change occurs in their similarities. So you have identical, bunch of identical, bunch of similar, bunch of different, bunch of unrelated, a little bit of grey area in the middle, and picking kind of the middle of that grey area as to where those changes occurred. Okay. Then what we did, we plotted that minimum discernible change that we calculated against the average standard deviation, coefficient of model correlation, and there was another one, ICC as well. And then also for each joint angle, and then the second variation as well, based on standard deviation against each of our criteria, each of our outcome measures. Then we look at, okay, our minimum clinical difference for our knee was 5 degrees. So 5 degrees here, up there, over here. Our corresponding average standard deviation was somewhere around 2 degrees. 5 degrees, knee flexion extension was our minimum clinical difference. Well, here it is. It corresponds to 0.99 5 or somewhere around there. We'll see shortly what it was. CNC, the same for ICC. So our minimum clinical differences that we decided on for the each joint range of motion, from these plots we can plug it in here and see what it corresponded to in the different outcome measures. And we did the same for where we decided that the boundaries between where curves were considered same, identical, similar, different, or unrelated. Those values as well could also feed in, so like same, different, unrelated, and get a corresponding average standard deviation, corresponding CMC, and another graph corresponding ICC. Okay, so what does that all come to? You end up with something like this for average standard deviation, 0 at the bottom, and an average standard deviation 0.39, which, okay, this is specific to each joint angle, where a boundary considered where changing between identical to similar, similar to different, different to unrelated. So there are those boundaries there, and then our minimum single change, our two definitions of them, one based on standard deviation, one based on non-hypoxia continental, also read off that plot, and we get a corresponding standard deviation representing our minimum clinical difference as well. One on standard deviation, one on 95% confidence interval, and one on standard deviation. So then when we calculate our curves, we get all these values, we can look, in this case it's the average standard deviation. Where does that fit? Same again, average standard deviation here, where does it fit? And you can basically map from your outcome measure where corresponding, where it relates to our criterion values. Okay? It's giving us an indication. I'll probably say it later in another slide, but I'll say it now, because we're looking at that, you're thinking this isn't perfect. It isn't perfect. And again, it's room for a lot of further research. There's going to be subjective differences on where similar, different, unrelated might be. And I'll accept that, sure. But if you're down here, in the middle of that, I'm pretty confident that anyone looking at it will say, yeah, they're identical. Those curves, there's very little difference at all between them. If you're in here, in the middle area, they're similar, they follow the same pattern, but there's a little bit of separation during the there's a bit of a separation, they're following the same kind of pattern. Here, they're different. They're starting to get away from one another. And then up the top, they're unrelated. Okay? We're looking at unrelated, different, we'd be looking at different gait patterns. Okay, you've got to think about gait patterns, unrelated gait patterns. This doesn't really represent the same movement pattern anymore. Well, that's different than unrelated. This boundary doesn't really matter here, because you shouldn't be out there anyway. If you are, you're in trouble, so it doesn't really matter whether you call it different or unrelated. But in here, it's probably, if you're going to stick labels on these boundaries, yep, there's a little bit of leeway there and a bit of, okay, so this is falling in the similar, but it's near that boundary, so okay, it's in that grey area between similar and different. That one is similar. Any lower, getting towards this, and it's in that boundary again, between identical and similar. So that's basically the criteria measures. Well, what happens to it? It's just a way of mapping our outcome measures onto some minimum, onto our minimum clinically important differences and our ratings of whether they're the same, different, or unrelated. Correlation stuff with the reverse. You have one at the top is identical, perfectly identical, going down, 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 and you have 0 way down the bottom. And again, you would look at, you've calculated coefficient of model correlation. Here it is, 96. Where does that fall? Just in here. 96. What's this around the right one? Is it 92? 92. Well, that's right. How much should be down in there? No, further down. But anyway, you get the idea. They map onto that same type of arrangement. But one thing becomes clear when you look at this. Correlations, another little key point here. CMC and ICC, they have problems. This is the largest range of motion, I call this one. This is knee flexion extension, then hip flexion extension, then ankle flexion extension. Then we go into the inter and external rotations, and then the abduction adductions. And these were the plots of their outcome measures against, in this case, ICC. Well, you see that they're insensitive to changes in our minimum discernible change or our similarity or differences in gait curves. So if we were thinking of knee again, if this was the knee, and our minimum discernible change was 5 degrees, we'd be here 5 degrees, we're here. This curve is getting these all curves are getting very horizontal here. That means that very insensitive. If you add error into your estimate, become very insensitive to changes that we're looking at, the changes in similarity or differences in gait curves. So they're very insensitive. Which means that all our values, our borders between identical and similar, and minimum discernible change, whether it's based on 95% confidence interval or whether it's based on standard deviation, are all up in here, between 1 and 0.995 or something. They're all the need. That means a little bit of error in your ICC or your CMC, and you could be anywhere along here, anywhere. So basically, they are not good measures for gait, assessing similarity or otherwise, or reliability of gait, cycle, joint angles. Okay? But basically, pretty useless. Okay? People are getting ICCs and stuff all down here and saying, oh yes, that's good, yeah, that's good. Where are they? They're way up here. This is where you should be, up here. If you're like 0.9, forget it. But very insensitive to changes in single change. Okay, a little variation here, a lot of variation here. So not very good at all as far as gait goes, and basically not reporting anything more on those ICC and CMC from here on in. But you do get up with a whole table. I'm not going to. That's the whole lot. That's a lot of graphs, a lot of stuff. But you've got all your joint angles. Where's the knee flexion extension? 5 degrees, and then you've got 2 variations on the minimum discernible change, and then where it's related to similar, different, or unrelated relative to standard deviation. If you plot all that data, you look something like this. Each identical, similar, different, unrelated, and the two variations in minimum clinically important difference. And it so happens, which is quite convenient, they lie more or less in that, and this is by chance, it just turns out this way, which seems quite good in hindsight, quite convenient, that they lie in that area which has been rated as similar. That was good planning or good luck or something. But anyway, and you also see that if you're basing your differences on the 95% confidence interval, so a group and another group under similar conditions, your average standard deviation, which corresponds to your minimum clinically important difference, like 5 degrees for the mean, is higher. Your average standard deviation can be higher and be acceptable. But if you're basing it on standard deviation, a single measure before, a single measure after, and you're basing it on 4 times standard deviation, your outcome measure, standard deviation, has to be a lot better. And that makes sense. You're down towards the similar identical area, whereas 95% confidence interval, you're around that similar different rating of curves. So that's kind of representative graphically of what's all come out of this. And again, ICC again this time is the reverse. And you see, especially for the flexion extension, they're all crammed up the top here. And internal external crammed up the top. Again, as with the previous one, that one, very much related to range of motion. This here, highest range of motion, next, smallest range of motion. So very much related to range of motion. Same here, same pattern, very much related to range of motion. The largest range of motion, smallest range of motion. But yeah, okay, problems, particularly with ICC, CMC, that it's very insensitive. You need very high values. So, criterion values. So what we've seen are limitations. I've mentioned this already. It's subjective. Going through rating all these curves. Okay, there's going to be some variation from raters, where they consider these boundaries to lie. So yeah, it's more of a region, regions here between. They have a confidence enough. If you're in here, you're identical. Here, similar, different, and unrelated if you're in the middle regions. Okay, so we've got all these criterion values. We're going to go through a systematic review. We are running a little. Okay. It's probably getting up towards 50 minutes the way we're going. But that's right, we'll have a break and then have another session. Systematic review. I'm not even going to go into the method of systematic review. It will take too long going through all that. But anyway, you had a search of databases, you had criteria, selection criteria, and then you had inclusion criteria. You went through abstracts, you went through those, you got your full articles, reviewed those, you extracted your data, you rated them all on a quality scale, you did all that stuff. But I'm not, that's a whole other day, that one. We're just going to go to the results. Right. Introsession, down here. Studies across there. There's a couple of them added in that weren't part of the literary review. This one is unpublished data with Springs, a little gold. And this is the study that we'll look at later in the second half of the presentation. The reliability I did probably about 5 or more years ago, using this method that we'll talk about soon. So there's a few extras that we have in there. The Springs, local one here that was tested, and my one. First of all, introsession down here. Just looking at knee, flexion extension, abduction, adduction, internal, external rotation. Same game, same answer set. High variability between studies. Okay, doesn't matter what it is. Large variability. Also, we've got the red, we don't want to be out here, we want to be in that band here. We're using the minimum clinically important difference based on standard deviations, are slightly higher. You want to be below that purple line, if you can see it there. And there are some studies below, and some studies right above with knee flexion extension. Abduction adduction, not so good. A couple of studies below, most on or above. Internal external rotation, again, one. Couple of studies below, but then quite a few above. So intra-session, not as good as you'd expect. There are some studies that give quite poor results. Unrelated gait, different and unrelated gait patterns for the same subject walking up and down. Where that's coming from, you've got to look at post-processing and what's going on there. Their smoothing, their filtering, their identification of markers. What's happening with this data? Is there something in there that's making a difference between the same person, the results from trial to trial, the same person just moving up and down? So highly varied, and some are quite bad. But some are okay, some are quite good. Highly varied. Okay, so we go inter-session now. Okay, they've been tested, come back another day, get tested, and in some studies another day you get tested. The inter-session reliability, our minimum clinically important difference now is based on standard deviation. Okay, it's dropped down to around the green line. Again, no study there. Knee flexion extension, inter-session is where you'd want to be. If you're doing a single examination, intervention, single examination. Okay, most are different or unrelated. For knee flexion extension, inter-session adduction gets worse. Internal external rotation gets worse again. A lot of what you could say is rubbish, and a lot of rubbish. These are very different. There's only one line which is close to this purple line where you want to be, and there's only a couple of mine. That's hardly any. Most, as you can see, have really deteriorated before poorly in the inter-session reliability of the knee. If we go on, inter-session again, we're not going to go through everything, it's just too much. We're just going to look quickly at inter-session hip, inter-session ankle, just to get an idea of what's going on there again. It's the same story. Big flexion extension, big variability, flexion extension, big variability, so a lot of variability. But poor. You want to be around here, there's very few down there. You want to be here, there's very few there. And none, very few near this line. It's where you want to be. Okay, a lot from a different unrelated area. So again, similar, identical, similar, different, unrelated. So like identical, similar, different, unrelated. So a lot in the different, unrelated. Okay. Well, I've just thrown this up because what is different and unrelated? What does that look like? Well, here's just an example. I've just pulled out some data. This is knee internal, external. Doesn't really matter what it is, really. But the 1.49. That's right in the centre of that band of different. Okay. So you've got kind of grey area and grey area. If you're right in the middle of that knee internal, external, different range, that's where that's line. So this is right in that middle band. This is on the other side of that band. It's not way out in the unrelated, but it's on the other side of that unrelated. It's in that band of unrelated. Yeah, but not way out the top. So we're looking basically at something which is right in right in here, in the middle, and just above in here. Not way out there, so different and unrelated. Different and unrelated. So that's what we're looking at. Literature review. Okay. Large variation reliability outcome measures, intersection. Okay. So what wasn't mentioned in there was the marker sets that we used. The most common one used was the Vicon clinical marker set. It was tested, and then there was also the Helen-Haynes modified marker set a few times. There was a couple of 3D gait, T3D gait. But large variation. There's no similarities between common marker sets. So you have to separate the marker set from the implementation. Now, two different things. It's incorrect to talk about with these systems, or these marker sets, as a marker set as being reliable. The marker sets aren't reliable. There's so much variability between the implementation, so that's an institute, a lab, and an examiner doing it, to other labs and other examiners doing the same procedure, that you've got to look at the reliability of the implementation. Okay, so it's a misnomer, it's just an incorrect way of thinking to say that a marker set is reliable when you look at these marker sets. So no current marker set can be said reliable. Okay, there's no consistency across implementations. But if you look at the implementations of the marker set, again, non-sagittal plane rotations, you've got to say they are not reliable. Therefore not suitable for three-dimensional motion analysis. I put a little bit down here just to cover myself, unless it is explicitly supported by a reliability study. So explicitly means that study, that examiner in that lab has a specific reliability study relating to them. And if they can show that these joint angles, non-sagittal ones, are reliable, then okay, yeah, we'll accept that. But otherwise, no. So no implementation of the current marker sets, non-sagittal plane rotations are suitable for three-dimensional motion analysis. Going on further, it was all amongst that data, but anyway. Introduction of things like the knee alignment device. Now you probably won't know what that is, but the CAD knee alignment device to try and align axes. Segment clusters fixed on the outside. 6 degrees of freedom models. All this stuff has not led to a meaningful change in reliability. If you look at those reliability studies, by the way, they were listed by year, from oldest to newest, and there was no improvement in reliability. It was just all the way across. So there's been all these additions that have come on haven't made any difference. They have not addressed key factors influencing reliability. And in some marker sets, T3 gait sticks out in this regard, reverting back to minimalist marker sets, and use of pointers and wands and various other things, I would view it as a backward step. It's made no increase in reliability, and it's only added time and effort with no reward. And in the reliability of this one, it's actually worse. If the marker sets that were tested, this would be rated as the worst one. It's going back to the kickball marker set, which was abandoned years ago because of that very reason. It was unreliable. So if there's no reliability study, then all non-sagittal rotations, hip and ankle, are considered meaningless. Which is probably a pretty big statement, those last two, about the reliability. But if you look at the evidence, take a critical look at it, you've got to say, well, I've got to say, these aren't reliable. Non-sagittal plane rotations. If you haven't got evidence, a reliability study backing it up, conclusions, whatever, based on those rotations, non-sagittal rotations, it's not valid. Okay? Which has big implications for research over the last 20 odd years. Okay? Gauge said this 2003. Nevertheless, now this is, it's not valid to assume, as authors seem to have done, that just because you install a 3D motion analysis system, turn it on, plug it in, that you automatically get good results. Now that's fair enough, there's no argument with that, but you've got to go further. So if the experts using current methods cannot get reliable data, then there's a bigger problem. Okay, it's never been touched on yet. So a major shift in marker set design and implementation is needed, with far greater understanding of the errors in 3D motion analysis. And that is the first session, so how are we going with that? A little bit over. So if there's any questions, to wrap up, we'll just have a few questions, you have a 5-minute break, And then we'll come and look at the second half, which is looking at whys and hows and what to do about it.
So that's looking at, I just wondered if you had a comment, Alan, on so that's looking at the gait cycle
Yes.
in its entirety
This,
in terms of reliability. And there are a lot of studies that look at points in time, like a peak of this angle because that's often the question they're looking at. Do you think the picture's any better in that regard, or is it worse, or is it the same?
No, well look, if you've got this, and you're talking about minimums and maximums, this hasn't addressed, this is addressed reliability studies looking at the whole gait cycle. There's another whole, the literature review addressed those. There's another whole set of reliabilities looking at parameters, kinematic parameters, like your step width, your step length, your maximum knee flexion angle, and all that kind of stuff. There's a whole other set of reliability studies looking at that. This hasn't even touched on those. But if you're looking at ranges of motion and maximum minimum knee abduction, adduction, internal external rotation, movements, ranges of motion, well then it's also going to be poor.
That's in studies
But
looking
I haven't
at
looked
gait.
at specifically. Non-sagittal.
Is that? But are you saying that that's in studies looking at gait, walking, where you're
Gait.
looking at
Gait.
points in time? The story is exactly the same.
I haven't looked at it specifically. I haven't gone through that.
Okay.
But based on this,
You'd
based
think it was
if
similar.
you're getting stuff like this with the same person walking up and down,
Yeah.
one session another, and this represents what then if you're looking at maximums and minimums,
Yeah. And then like for movements that might be thought of simpler, where you might have someone doing a landing or some other movement that's not quite as complicated as a complete gait cycle, you would think that it would still be pretty poor, or you haven't looked at it?
Yes, before. It'll be relative to the range of motion. We'll see why later. Okay, this has looked at gait. The whole thing is gait. If you're looking at landing, jump landing, if you're looking at sidestepping, if you're looking at sprinting, if you're looking at a whole another lot of studies of critical values, range of motions, and hadn't even looked at to see what's relevant for that stuff. The whole thing of this is just gait. It's a fundamental measure collected all around the world, and so it's gait. But you can look at this and you can judge, okay, how's this going to influence other movements?
Your
how it
threshold
relates.
of how you relate it, like different, unrelated and stuff for another movement, that might shift a little bit based on that.
Well, the best you could do, I suppose, is say, look at the range of motion and say, okay, that range of motion is more close to the knee, or maybe the hip adduction action has a closer. No, but even that, it's not. Trying to get those critical values to transpose to another movement pattern will be different, because the shape, expected shape, is going to be different. And so it's not really that applicable to other movements.
Yeah.
Yeah, so it's a whole lot more work. But the thing is, the aim here is to look at gait, and for the basics, to get a method, an approach, and understand reliability errors, where they're coming from, so that we can get a reasonable estimate of gait kinematics. Yeah, the other movements, it's a whole yeah, further study and research. Yeah. All right.
Take a break.
Yeah, take a break.
10 minutes?
10 minutes, okay.
Oh.